Alrighty, folks. So today we're going to be talking about section 9.1, which is some more confidence interval stuff. But today we're going to be using confidence intervals to compare population means. Right? So we're going to be comparing two different populations, or the means of two different populations. So we're going to call them mu1 and mu2. And we're going to do this in a situation where sigma is known and the populations, or sorry, not the populations, the samples specifically are independent. So the other option there is, of course, for them to be dependent, and that means that the individuals are linked in some way, right? If one sample, if say you're doing a study on twins and one of your samples is one of a pair of twins and the other one is the other of a pair of twins, obviously individuals in your sample are linked by being twins. If you are doing a study about how something might change a person's views, then perhaps you might take the same individuals and ask them a question before you tell them something or do something with them, and then ask them the same question after. Then your samples are linked by being data given by the same person, right? So in this case, these are going to not be what we're dealing with. So first we're going to deal with independent samples. So there's nothing linking individuals from our two different samples. And we also want to make sure that we know sigma. And in that case, so our population parameter for these sorts of problems is mu1 minus mu2. Check real quick. Okay. Our point estimate is going to be x bar 1 minus x bar 2. So here we have two different populations. We have population 1 and population 2. And we're looking at a sample from each of them. And we want to figure out the difference in means of the population, and we're going to do that by considering the difference of means of the sample. Now, the order here doesn't make any difference, right? I did 1 and then 2 because that's sort of the order we expect. You can do 2 and then 1, as long as these guys' order must match, right? In some problems, maybe you don't even call it 1 and 2. Maybe it's old and new. Maybe it's labeled by color. Maybe there's some other important label, but as long as the order matches, that's what's important, right? And that all the things from one sample have the same subscript, right? In this case, N1 is the size of the first sample, i.e. the one associated with x bar 1. And again, it doesn't necessarily need to be labeled with numbers, right? If you had x bar old and x bar new, then you would have n old and n new, right? The subscripts just associate it together. And N2 is the size of the second sample, right? Same sort of idea there. And we want to note that for these types of problems, we want N1 and N2 to be greater than or equal to 30, or the populations must be normal. Right, so same as we had for section 8.1, except for both ends must be bigger than 30 or both populations must be normal. Right? And in that case, we're still going to have C equals the confidence level. Alpha is still going to be 1 minus C. So we're still in that same situation. And our confidence interval is going to look just like it did before. It's going to be the point estimate minus E, and then the point estimate plus E, right? So the exact same point estimate, plus just minus E the first time and plus E the second time, exactly the same way as we've been doing before. And then, so this should be sigma 1 and 2, and it should be R. Sorry. I just realized I hadn't put both sigmas there, right? So, of course, what we really need to know to be able to do these is what is the formula for E? And it's very similar to section 8.1, except we got to get both of those sigmas in there. So we still have Z alpha over 2. And instead of just taking the square root of sigma squared, we're going to do the same thing for both of them and add them under the square root, right? So we're not going to take what we would have for the individual ones and then add them together. We're instead going to add them under that square root. Z alpha over 2 comes from that same table we've been dealing with. There's another copy of it, table 9.1.1. It's the same table as table 8.4.1 and 8.1.1. And I actually just copied the 8.4.11 example to this page. So when we use that, we'll want it. And again, right, we are going to be C% certain that mu1 minus mu2 is in the confidence interval, right? And so there's some specific things that we're generally going to want to take away from that. Usually we don't really care what M1 minus M2 is. We want to know how to compare M1 and M2. So it turns out if 0 is in the confidence interval, then mu1 minus mu2, mu1 might be the same as mu2, right? This is sort of the trickiest one, because we can't say that we are C% certain that mu1 is equal to mu2, right? We just know that it's in there. 0 is in there, but we're not our confidence level percent certain that it's going to be 0. It's just going to be somewhere in there. So this is one of those situations where we might say something like, we don't have any evidence that suggests that they are different. All right, so that's how we often like to phrase it. So we don't have evidence to suggest they are different. So we're not a certain percent confident that they're the same. We just don't have any evidence that they're different. Right? If 0 is not in the confidence interval, that either means that both endpoints are negative or both of them are positive. Right? If one of them is negative and the other one is positive, then 0 is going to be in the interval. So one of the other options is if both endpoints are negative, right? In that case, we are C% certain that mu2 is bigger than mu1. Right? Because if mu1 minus mu2 is negative, which we are going to be C% sure that it is in this case, then whatever one you're subtracting is the bigger one. Right? So if when you subtract two numbers, you get a negative number, the one that you're subtracting from the other is the bigger one, And if both endpoints are negative, we are C% certain that actually mu1 minus mu2 is negative. Right? And similarly, if both endpoints are positive, we are C% certain that mu1 is bigger than mu2. Because for that to be the case, that would mean mu1 minus mu2 is positive, and if both endpoints of our confidence interval are positive, we are C% certain that mu1 minus mu2 is positive. Right? So those are usually going to be how we use this type of confidence interval. Right? The confidence interval itself, right? This statement is not usually what we're focused on. We're focused on whether 0 is there, or they're both negative, or they're both positive. Because what we really want to say is whether or not one of them is bigger than the other. Right? So let's do some word problems. So first off, I'm going to bring our table up here so we can reference it. And then I'm going to be paranoid. Okay, good. I'm going to drag this guy up here. I had some difficulty finding some good problems, some good data to use. So this one in particular that we're going to do first isn't quite perfect. It doesn't actually have sigmas as written, but we're going to pretend like they're population standard deviations. Alrighty. So here we have two different populations labeled by 1 and 2, right? So we're probably going to use mu1 and mu2. And we can start pulling out data. This first sentence is all about sample school 1. So everything we find from there is going to be subscript 1. So first off, sample of 60 tells me that N1 is equal to 60. The sample has a mean weight of 55. Tells me that the sample mean, sub 1, is 55. And with a population, standard deviation, like I said, we're going to assume that it's a population 1. Because I forgot to type that part of it out. So we're going to assume that the population standard deviation of school 1 is 5 kilograms. Right, and one thing to note is that the units don't matter too much for our purposes. We've got enough to worry about without dealing too much with conversion of units. But the important thing to pay attention to is to make sure that your mean and your standard deviation have the same units. And they do, so we're good. Right, so this second sentence is all about sample 2. So it's of 50, so N2 is 50. It has a mean of 53, so X2 bar is 53. And again, it has a population standard deviation of 7, so sigma 2 is 7. Right, our confidence level is given here, right? A 95% confidence interval tells us that we want C to be 95%, right? Which tells us that alpha is going to be 0.05. For the Z table, right, either of those numbers is fine. We don't necessarily have to find both. If we were using the T table, then we do want alpha, but since we're using the Z table, we're fine. Okay, so for the difference of mean, so that tells us that we're in this section. So we need to look at E. That's going to be Z alpha over 2 times the square root of, let me write it out first, sigma 1 squared over N1 plus sigma 2 squared over N2. That order, again, really doesn't matter. As long as the 1s are on top of the 1s and the 2s are on top of the 2s. Right, so this is Z 0.025 times the square root of 5 squared divided by 60 plus 7 squared divided by 50. Now first let's find that z value. And so we go up here, we want alpha 0.05, right? That matches up with our 95% confidence level, so we know we got that right. We go over here, and it's going to be 196. And then we take this number and we plug it into our calculator. 1.96 times the square root of 25 divided by 60 plus 49 divided by 50. All right. That gets us 2.316. And so now we know that our interval is x1 bar minus x2 minus e, x1 bar minus x2 plus e. So this is going to be 55 minus 53 minus 2.316, and 55 minus 53 plus 2.316. So this is going to be negative 0.316 and 4.316. Right? So, that's our 95% confidence level. That's all this problem asked about, right? But if we think back to our three different options here, 0 is in the confidence interval, right? We go from a negative to a positive, means 0 is in there. So we do not have enough evidence to suggest that the two schools have a different mean weight. Right? Seems like students at the schools probably weigh about the same thing. Right? There's a little bit more on the positive side, so if there is a difference, it's that school 1 is heavier, right? But we don't have enough evidence to know that for certain, right? We can't even be 95% certain of that because 0 is in there. We just don't have enough evidence to suggest that they're different, right? So let's do this problem. And I had to do some editing here because my subscripts didn't come through. So this is another reason why we might compare some things, is to figure out which of two different television companies gets a better score, right? So in this case, we have 1 and 2 again. I probably should have picked an example where we can label it by something else, but we have Company 1 and Company 2. Both of them made random selections and rated their cable companies on a 5-point scale. And they're looking at the averages of those scores, right? So the average satisfaction level. So we need to set up all of our information about Company 1, and all of our information about Company 2. And this problem was just nice and obliging enough to go ahead and lay out what all those values are. Right? The ends we could have figured out from here and here, right? But the rest of it, it just gave us the data flat out. So it wants a 99% confidence level. So alpha is going to be 0.01. It's looking for a confidence interval for the difference of means, so we know that we're in the right section. And this is just explaining again what all of those values are about. So we need to figure out E. That's going to be Z alpha over 2 times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So it's going to be Z 0.005 times the square root of 0.51 squared over 174 plus 0.52 squared over 355. So first let's find that Z sub alpha over 2. Right? Remember for this chart, this is what we're looking at. If it was the T chart, we look at the subscript. But for this chart, we're looking for these guys. So 99%, 99% matches up with this one. So we did get our C and our alpha associated correctly, which means that the Z-score we want is 2.575. So 2.575 times the square root of this stuff. And this is a good calculator time. So I'm going to plug in all of these values. All right. And my calculator gives me 1,223 when I plug all that in. Yeah, looks like it. So that means that our confidence interval is going to be x bar 1 minus x bar 2 minus E. X bar 1 minus x bar 2 plus E. So that's going to be 3.51 minus 3.24 minus 0.1223. And 3.51 minus 3.24 plus 0.1223. So let's do this in pieces. This is going to get 0.27 minus 0.1223. And this is also going to be 0.27. So one thing that you can do as an intermediate step is go ahead and figure out up here, right, that your point estimate is going to be right, and just have that to fill in both of these places, because it's always going to be the same, and it's going to be the same number subtracted by E and added to E. So we get 0.1477, if I did that correctly in my head, and 0.3923, right? So we are 99% certain that the mean lives in there, right? But remember, of our three options, right, both endpoints are positive, right? We got two positive numbers. So we are 99% certain that mu1 is bigger than mu2. Because mu1 minus mu2, we're 99% certain that that's going to be a positive number. and that means that mu1 has to be the bigger one, right? So that's how we interpret these sorts of things. It's the same process as we've been going through as far as finding them. We just have a slightly more complicated formula. But once we get all the numbers, we're just going to throw it into the calculator anyway. So that's fine. Right? So we're going to continue on in this path for a little bit longer. We got to figure out what to do when we don't know what sigma is. I'll give you a hint. It involves T, and also some slightly more. Well, no, it involves T. That's the basic thing, and then we'll keep going. We have a couple other things to do there, but that's for next time, and I'll see y'all later.